Okay, so welcome everyone. Thank you for joining. We are resuming the TVS Science Colloquium series today. We will have the great pleasure to listen to Kevin Burdge. I hope I'm pronouncing your name correctly.
Yeah.
He's a postdoc at MIT. He will start a faculty position at Stanford next year. Is that correct? So yeah, congratulations. He will tell us today about identifying and characterizing minute to hour timescale compact variables. So please, Kevin, take it away.
All right, thank you. So yeah, I'm excited to be giving this talk. I've been thinking a lot about how to do exciting science with Rubin. And so what I'm going to be broadly talking about are discovering sources of millihertz gravitational radiation using visible light from synoptic surveys like LSST. And I'm just going to dive right into it because I have a lot to talk about in the next 40 to 45 minutes. Let me get this going. Okay, so just a brief recap of gravitational waves for those here who are not gravitational wave astronomers is gravitational waves are basically self-propagating perturbations in the space-time metric that are generated by the evolution of the quadrupole moment of a mass distribution. And we have built detectors like the LIGO detectors, which are sensitive to measuring basically these perturbations in space-time. Most detectable gravitational waves that we can detect with our current detectors originate from two extremely dense objects orbiting each other. That's a very good way to get a time-evolving quadrupole moment in general relativity. And so, for example, LIGO has been sensitive to the mergers of black holes and neutron stars. And they're pretty exciting, like gravitational waves, because they give us a completely new way to study some of the most dense objects in the universe. So what I'm looking for are these gravitational waves in the millihertz frequency regime, which are a little different than the gravitational waves that many people are familiar with from LIGO, which are at much higher frequencies. And so there's currently a space-based detector for millihertz gravitational radiation called LISA that's under development by the European Space Agency. It will revolutionize the gravitational wave world because it's going to probe lower frequency regimes than are accessible to LIGO. And that's really exciting because when you look at the frequency regimes that LIGO can see, so these high frequencies at hundreds of hertz, you're really only seeing objects whose distances are measured in gigaparsecs. Like they're very, very far away from us, the merging black holes and neutron stars that we see. But what's exciting about LISA is it's really going to be probing sources of gravitational radiation in our own backyard, in the Milky Way. We expect to see thousands of sources of persistent gravitational radiation in the Milky Way. And you'll probably notice in this bottom bullet point that I italicized the word persistent. And what I mean by persistent is these are not transient events where you just see a merger and they're gone. They're steady state sources. And I really like steady state sources because you can characterize them. You can decide that you need to build a new detector to study this one really exciting source you found, and you don't have to worry about it merging and going away on you. These things will last for at least tens of thousands of years before they merge in most cases. And so let me talk a little bit about this gravitational wave frequency band. So here's a plot of the characteristic strain on the y-axis, which you can sort of think of as like an amplitude of the gravitational wave versus the gravitational wave frequency. And the thing I want to emphasize is these three black curves you see are basically different ways we have of detecting gravitational waves. So on the left, on the long frequency regime, we have these things called pulsar timing arrays. I'm not going to get into those in this talk. But I want to point out LIGO you see up there with its peak sensitivity at about 10 to the 2 hertz. That curve does not overlap the LISA curve. And what that means is these are two really complementary detectors. They're looking at different parts of the frequency space. And the types of astrophysical phenomena that one can see do not fall into the frequency band of the other. So it's not just like LISA is a better LIGO. LISA is a completely different type of detector, and they both have their own unique roles. And the particular class of astrophysical sources I'm going to be talking about in the remainder of the talk are these resolvable and unresolvable galactic binaries. So these are binary systems in our galaxy with orbital periods under about an hour. And so let me talk about what these gravitational wave sources actually are. Most of them are white dwarfs, pairs of white dwarfs. And so just a brief recap on white dwarfs for those who aren't too familiar with them is they're the extremely dense leftover cores of stars like the sun. The vast majority of stars at the end of their evolution will leave these behind as their stellar remnant. And they're about the size of a rocky planet, to give you a sense of scale. Hello? I wasn't sure if someone was asking a question. So to give you a sense of scale, they're about the size of rocky planets like the Earth, but they have stellar masses. And that means we're talking about densities on the order of about 1 million grams per centimeter cubed. So this is matter that is far more dense than what we're used to in our daily lives, though significantly less dense than in a neutron star or a black hole. But the reason that white dwarfs are kind of neat is we actually think we understand their equation of state pretty well, and that it's well approximated as a degenerate Fermi gas. And one of the reasons that's really nice is you can make plots like this. So in the upper panel, here's the radius of a degenerate Fermi gas as a function of its mass. And you can see as it becomes more massive and gets close to the Chandrasekhar mass, the radius continues to drop off. But I want to draw your attention to the bottom plot, which is recasting that equation of state now in terms of the density of a degenerate Fermi gas as a function of its mass. And you can see the density goes up as you get close to Chandrasekhar mass. And the reason it's really useful to recast this equation of state in terms of density is the following. So if you don't remember anything else from this talk, I would encourage you to remember this equation because this is really, really cool. And people who work on binary systems use this all the time. And it's this remarkable property that the orbital period at which something overflows its Roche lobe in units of days. And before I explain the rest of the equation, let me just define Roche lobe. So in the upper right-hand panel here, you can see a diagram of two objects with these contours that represent gravitational equipotentials. And the Roche lobe is basically that inner contour. And so what it means to fill the Roche lobe is that star on the right you see there is close to filling its Roche lobe. It fills its Roche lobe when its radius gets so big that it can no longer fit in that potential. And basically what will happen at that point is matter will start leaking through the Lagrange point onto the other compact object, basically accretion. And so this equation is saying the orbital period at which an object will overflow its Roche lobe in units of days is approximately equal to 0.43 divided by the square root of the density of that object in grams per centimeter cubed. And what that means, it's actually kind of cool, is say I take the sun and put it next to a black hole. It will overflow its Roche lobe at about 8 hours. And the reason is the sun has a density of about 1.5 grams per centimeter cubed. Say I now take the sun and put it next to a white dwarf that's 10 times less massive than that black hole. The sun doesn't care. The sun fills its Roche lobe at 8 hours. So what it's saying is the minimum orbital period that an object can fit into is set by its density. It's actually rather insensitive to what the other object is that it's orbiting. And so now what we can do is take this bottom panel of density versus mass for degenerate Fermi gases and convert that into a characteristic orbital period at which a degenerate Fermi gas will overflow its Roche lobe and interact with its companion. What I want to remind you of is now you can see why LISA is a really natural tool for probing white dwarfs which overflow their Roche lobe and interacting with their companions, because if you take 2 divided by those orbital periods, you end up with millihertz frequencies, which is exactly where LISA's at its peak sensitivity. So LISA is really a perfect machine for studying merged white dwarfs. So now I've told you why LISA is great at finding these pairs of white dwarfs, but you might say, hey, you just told us we understood the equation of state for these. What's so exciting about white dwarfs? Like, why do we care? So let me motivate physically why these objects are so interesting. One of the reasons is by studying pairs of close white dwarfs, we can actually constrain the binary evolution processes that help form compact objects in binaries. So, I mean, one of the biggest questions now, thanks to detectors like LIGO, is how do compact objects, whether they're white dwarfs, neutron stars, or black holes, end up in orbits that are so close together that they're able to merge by emitting gravitational radiation? Because if you start out two black holes in a one-day orbit, they will not merge in a Hubble time. They are not emitting enough gravitational radiation to do that. You've got to get them to a shorter period. And so we think there are these common underlying physical processes like common envelope involution and stable mass transfer that might allow such systems to form. And the nice thing about this huge sample of gravitational wave sources in our own galaxy is that we can actually use them to constrain these processes quite well. I should also mention that these objects are one of the keys to understanding the physical mechanism underlying type 1a supernovae. So there's certainly widespread consensus that type 1a supernovae come from the explosion of a white dwarf. And type 1a supernovae are sort of a big deal, right? They were the standard candle that was used to demonstrate the accelerating expansion of the universe. But I would say sort of one of the sort of dirty secrets of the white dwarf community is that even though there's consensus that these originate from exploding white dwarfs, there is certainly not consensus on the physical mechanism that actually causes most of these white dwarfs to explode. And broadly, there are sort of these two categories, the double degenerate channel, in which you merge two white dwarfs or get two white dwarfs to interact to cause the explosion, or the single degenerate channel, where you have a white dwarf close to the Chandrasekhar mass accreting from a non-degenerate companion. And so one of the keys to understanding the origin of type 1a supernovae is to study this double degenerate population. And it turns out that LISA and current time domain surveys are a really powerful way to do that. And I should mention, here's a picture of the single degenerate channel. These surveys are also really, really useful for studying the single degenerate progenitors, such as cataclysmic variables. And lastly, I think one of the interesting things too is we can use some of these double white dwarf systems to test the equation of state of these compact objects, which we think we understand quite well, and probe accretion physics in a unique regime. And I should say, one of the reasons I really like merging white dwarfs too is I just told you this story of how some of them maybe end up as type 1As. But there's actually a lot more to the picture than that. So this diagram here on the right shows you all the different outcomes we think that might originate from merging two white dwarfs as a function of the mass of the two white dwarfs. And you can see this is a pretty colorful plot with a lot of different things written on it. I'm not going to go through them all. I just want to say that this is really rich astrophysics. I mean, when you merge two neutron stars, you get a kilonova, maybe a black hole remnant. When you merge two black holes, you get another black hole. There aren't too many things that can happen in those phase spaces. Here, you've just got this enormous phase space to explore where the outcome changes radically as you dial the masses of the two white dwarfs up and down. And so that's one of the reasons this population of objects is also pretty fascinating. And one example of merger outcome that we've actually been able to study with some time domain surveys is Ilaria Caeso led a write-up of this object that we found in ZTF. This was a white dwarf that was just barely bigger than the size of the moon. It's one of the most massive white dwarfs known. It's so massive, we think it may still collapse into a neutron star. And it's also highly magnetic and rotating every 6.5 minutes. And we think it's because it's actually the remnant of the merger of two lower massive white dwarfs that didn't explode as a type 1a supernova. So current surveys are not only great for finding the double white dwarfs, they're great for finding some of these merger remnants. So let me stop talking about the gravitational wave background and all of this and just get to the photons now and what we can do with things like LSST and other current time domain surveys like ZTF, ATLAS tests, and so on. So a lot of my work has been based on a survey conducted at Palomar called the ZTF, the Zwicky Transient Facility. which is based on that little 48-inch Samuel Ocean Schmidt telescope you see there on the left. And that telescope's really kind of the start of this observatory because it's a Schmidt with an enormous focal plane. So the focal plane's about 50 square degrees, and ZTF is basically a large array of CCDs designed to take advantage of that full focal plane. That's kind of critical in what makes ZTF quite powerful because it allows it to accumulate a lot of images of the sky very, very quickly. And there are other surveys, by the way, currently in development inspired by ZTF. For example, this is the survey LS4 being developed by Berkeley, which will be based on the ESO Schmidt in the Southern Hemisphere and is designed as actually a complement to LSST. But let me just mention that of the surveys you see here on the right, you're seeing pictures of the focal planes of all surveys that are as deep or deeper than ZTF. And something I want to note is ZTF's field of view is quite exceptional for the depth that it reaches. But LSST is really an exception on this plot because what you don't see with just the field of view is the volume that these surveys can reach. And because LSST is based on a 6.5 meter aperture as opposed to a 1.2 meter, you're able to access far more stars with it. And so it's really quite remarkable that we're able to have a survey on such a large aperture with that 10 square degree field of view. And so a lot of what I'm going to be talking about here that's been done with ZTF, I'm going to show you what we can do with LSST as well along these science cases. And so let me talk about what I actually do. What I do is I take light curves, whether it's of stars, every star in the sky, say 2 billion of them that we've detected with LSST, and I Fourier transform them. And I try to look for orbital frequencies corresponding to minute periods. And people will often stop me here and say, wait, Kevin, your survey has a 50 square degree field of view, but if you're trying to do the whole sky, that means you're only going to get a visit in maybe once every night or two. Haven't you heard of something called the Nyquist frequency? How are you expecting to pick up minute timescale periods and data that's sampled every few hours? And well, the answer is that, so here's a diagram showing where the Nyquist frequency comes from. The Nyquist frequency basically comes from the fact that when you convolve your signal with a periodic window function, you get what we call aliasing in the output. That makes it very difficult to find frequencies that are very, very high compared to your sampling rate. But there's this beautiful property that when you randomly sample your data, that symmetry in the window function vanishes. And what that means is that you no longer get aliases associated with the Nyquist frequency. There's effectively no Nyquist frequency in randomly sampled data. And it just so happens that these surveys like LSST and ZTF and ATLAS and so on are effectively randomly sampled. And what that means is we're actually sensitive to minute timescale signals and data that's being sampled once every few days or less. And I basically exploit that property to look for these signals. That's not easy to do, however. It takes some pretty intense hardware. And so I spent a lot of my PhD developing algorithms on graphics processing units for this task. And the reason that it takes some intense hardware is if you're looking for minute timescale periods and data that's been sampled over years, you have to search huge frequency grids. We're talking about something like 10 to the 7 trial frequencies per object. And when you're doing that for 10 to the 9 objects, each of which have 10 to the 3 timestamps, you've got a lot of floating point operations to get through. But it just so happens that GPUs are a great tool for getting through that many floating point operations. And so I designed a lot of my own computer hardware to do this. So this is a box I built in graduate school, which is basically just a ZTF light curve mining box. I'm sure a lot of Bitcoin miners would have loved to have this, but it was too busy doing science. But one of the interesting trends that's happened with GPUs is that they continue to get more powerful, which actually makes me quite optimistic that handling an LSST scale survey will actually be not that difficult. One of the interesting properties, though, is as they get more powerful, they also get larger. So this is the first GPU I bought when I was young. It was like in middle school at the time. This is the one that I currently have in my desktop. I just recently bought a new one. This is a picture of it next to my son. They're now larger than newborns. And if the trend continues, they'll look like this soon. And this is because you're needing to dissipate more and more heat because these things are drawing an enormous amount of power. Because effectively what a GPU is a massively parallelized piece of computing hardware where you can sort of think of it as similar to how a CPU has multiple cores. A GPU takes that to the extreme and goes to thousands or even tens of thousands of cores, running at slightly lower clock rates than what you would see on a GPU. Or on a CPU. And that makes them exceptionally powerful for highly parallelizable operations like Fourier transforms. And so that's basically my bread and butter, is I use these tools to do massive scale Fourier transforms on large astronomical surveys. So now let me talk about what I've been finding using these types of transforms. So with ZTF alone, I've discovered over 20,000 objects that exhibit coherent periodic flux modulations at shorter than a half-hour period. These encompass many detached and accreting double degenerates, so those double white dwarfs I was talking about. But I just want to say, when you do these searches, you find a lot of other cool things. For example, rapidly rotating, highly magnetic white dwarfs called intermediate pulsars that are accreting from companions. Pulsating white dwarfs, pulsating hot subdwarfs, rapidly rotating highly magnetic white dwarfs. I don't have time to get into all of these, but I just want to say it's a rich phase space when you look for minute timescale periodicities in these surveys. And it's led to a lot of very exciting work over the last few years. And we have a backlog of objects still that I just haven't had the bandwidth to write up. So now I want to get to the good stuff, though, which is near and dear to my heart, which are the double white dwarfs. So here are 15 of these that I discovered with ZTF data over the course of my PhD. And so I want to talk about what causes periodic flux modulations in these objects that allows us to detect them. There are really three main physical phenomena underlying their periodicities. One is that many of them are eclipsing, and you can see lots of examples of eclipsing sources in this plot. And basically, an eclipse happens when one object passes in front of its binary companion and attenuates the flux as a result. It's just a geometric effect. But another effect I want to talk about, which is a little bit less well known, is something called ellipsoidal modulation. So you can see it in the top row there, that 20.6-minute object's a nice example of it. This is a sinusoidal modulation that occurs at twice the orbital frequency. And what it actually arises from is the tidal deformation of an object. So let me show you a little movie to illustrate that. So the movie on the right shows this ellipsoidal modulation effect where you see that larger yellow-looking white dwarf in the lower left-hand panel is kind of being deformed into this ellipsoid shape. And you see a flux modulation because you basically see different cross-sections of it over the orbit. So you're seeing a larger cross-section that shrinks down to the circular one that goes back to the ellipsoidal one, and that's what gives you the modulation. And those sources are particularly interesting because if you have a white dwarf orbiting a black hole or a neutron star, you would never expect to see an eclipsing signal out of that, but you certainly would still expect to see ellipsoidal modulation if the white dwarf were close to filling its Roche lobe. And then, of course, on the left, you have an example of an eclipsing source. And there's another type of modulation that you can see in that source that comes from one of the objects irradiating the other. So that's what gives this quasi-sinusoidal modulation out of eclipse. And that's pretty easy to understand. It's just like a day-night cycle of that yellow white dwarf you see is much hotter than the cool blue object in the movie. And what's happening is that very hot object is irradiating the surface of the cooler companion that's facing it. And so as you see the day and night side of that object rotate in and out, you get this extra sinusoidal modulation on top of the eclipses. And so these are the physical, the underlying physics that's giving us the periodicity that allows us to detect these in time domain surveys. I also just want to say a big part of the program too is spectroscopically following up these objects. So here's a collage of spectra from those objects. I'll just point out that there's a lot of rich information in these. Many of these you see just hydrogen absorption lines, for example, that 23.7 minute system on the left. But some of them you see the story is more complicated, like just under that object, the 37.3 minute system, you see there are more lines there. Those are helium lines, and that's telling you something special about the evolutionary history of this object. I was mentioning earlier we can use these to constrain evolutionary processes like common envelope evolution and mass transfer. And this is one of the ways, by looking at the spectra of the objects and seeing what's actually happening and whether the hydrogen's been removed from their surface. And I'll note that we're also sensitive to accreting sources. So you can see in the middle column, there are actually two sources that are dominated here by helium emission lines. We call these AMCBNs, and those are actually actively mass transferring, and you're seeing an accretion disk. And so what I want to do now is take a step back. I've just shown you that we can find these with surveys like ZTF, and I'm going to convince you in a few minutes that LSST will be great for these too. But what I want to take a step back and talk about is what can we actually measure with these objects? Well, one thing you get with these objects is they're emitting gravitational waves that we can detect with LISA. And those gravitational waves deform space-time in two special ways. So here's one example of one of the gravitational wave polarizations of what is happening to space-time, the actual change that we're measuring. And by measuring the gravitational waves, what you get is you get an inclination constraint because each polarization has a unique inclination dependence, and I'll show more of that in a moment. And there's also this amplitude coefficient that depends on the chirp mass of the binary, its gravitational wave frequency, and also crucially the distance. Those are kind of the three free parameters here from the gravitational wave amplitude. And as I mentioned, by using the two polarizations, which have different dependencies on orbital inclination, you can measure the inclination directly from gravitational waves. But what I want to talk about are the electromagnetic waves and everything that you can do with them. And so I want to play this movie in the bottom here. This is real data of a binary I discovered, which has an orbital period of 6.91 minutes. This is taken with a high-speed emitter called HyperCam on the GTC. It's a 10-meter class telescope in La Palma. You can see it in the lower left-hand quadrant of that movie. It's the thing that's disappearing periodically. So imagine getting that signal simultaneously with seeing the gravitational waves with LISA. And I want to talk about all the things you can do with that signal. And I'm going to spend the next several slides doing it. But one of the obvious things, of course, are inclination constraints you can independently get from a signal like that by looking at the eclipse geometry. But in addition to that observable, another thing you can see are the time evolution of the spectra. So here are spectra taken with LRIS on the Keck Observatory of that exact object. And what you can actually see are the emission lines within those absorption lines Doppler shifting over the course of those 7 minutes. So you can also use the spectra and how they're evolving over time to constrain the masses of the objects, for example, using things like Kepler's laws by studying the Doppler shifts of those lines. And so you're getting all of these signals at the same time with these objects. So you want to talk about exciting multi-messenger science. To me, this is really exciting stuff to be able to use all of these signals synergistically together to make measurements of the objects with exquisite precision. So let me talk about some of those exquisite precision measurements using this HyperCam light curve of the 6.91 minute binary. And so just by looking at the light curve alone, and by the way, the reason I'm emphasizing light curves is Rubin's going to deliver these on an absolutely enormous scale for a huge number of sources. So I want to talk about everything that you're going to be able to learn from just these light curves alone, without even thinking about the spectra or the gravitational waves. So just by looking at the light curve, one thing you see is this modulation out of eclipse, the sinusoidal one. I mentioned earlier that comes from a day-night cycle in the companion. So it's kind of telling you one of these objects is irradiating the other. And you see a shallow secondary eclipse at the peak of that irradiation is basically the heated day side of the cooler object is getting blocked by the other white dwarf. But the real star of the show in this light curve is this deep primary eclipse. And so just looking at that eclipse, let's talk about all the things we can infer about the system. Well, one thing that we can almost immediately read off is that the inclination is close to edge on, because you don't get a full eclipse like that unless you've tuned the inclination so that one of the objects is totally able to occult the other. And by modeling it, you can actually pin down that inclination measurement to better than 1/10 of a degree. The other thing you can infer is, let's say this object that's being blocked during that eclipse is object 1. You can infer that the temperature of object 1 is much, much greater than the temperature of object 2. And the reason is because of how deep that eclipse is. It's telling you that object 1 is contributing most of the electromagnetic flux, and that's because it has a much higher surface temperature than object 2. That's something you would never get with gravitational waves, but you can read off of a light curve almost immediately. You can also infer that hot object number 1 here is smaller than object 2. And the reason is that eclipse is total. It's going to basically zero flux. And what that tells you is object 2 is big enough to completely block object 1. And that's only possible if object 2 is bigger than object 1. And then you can use a white dwarf mass radius relation to say, well, I know that smaller white dwarfs are more massive than bigger white dwarfs because of the equation of state. So you can even infer that hot small object number 1 is also the more massive of the two. This is just by looking at the light curve. We haven't even done any modeling here. And imagine being able to read off that much information just on a massive scale using all of these things we find with LSST. And of course, by modeling the light curve, you can do much better than just write down inequalities. And then there's some other cool physics you can constrain by, for example, zooming into the bottom of the eclipse. You can actually see that the signal doesn't actually go all the way to 0. And what we're seeing there is the night side flux of object 2. And that's actually quite interesting in this case because we can infer the temperature of object number 2 that way, which we estimate is about 5,000 Kelvin here. That's already challenging things like tidal physics. So state-of-the-art tidal models by Jim Fuller at Caltech predict that this object should be tidally heated to about 15,000 degrees. Yet we measure a temperature of only 5,000 degrees using that eclipse. That's a big discrepancy because a 15,000 Kelvin blackbody radiates a lot more energy than a 5,000 Kelvin blackbody. So something is up with the tidal models here and how efficient the dissipation is. I should mention, though, that the uncertainty in that temperature is quite large. And I'm not going to show it in this talk, but I'll just say there's been a James Webb program that's observed this exact source, and now we have a much better temperature estimate of the secondary from that. I should say, too, studying these objects at other wavelengths is extremely rich. So you can look at them, for example, in the ultraviolet. And so here's that hypercam light curve again of this object. Here's what it looks like with HST costs. There's some cool physics manifesting here, and it's that reprocessed radiation from the day-night side cycle doesn't really show itself in the ultraviolet. And that's just reflecting the fact that that cooler white dwarf is reprocessing the flux from the hot white dwarf at its own blackbody temperature, which is too cool to emit significantly in the ultraviolet. So these are all the things you can do with light curves of one of these sources, multiband light curves. But you can do even more. You can time the eclipses. So you can watch how the eclipse time evolves over the course of, say, a decade. And let me briefly explain this plot. For those of you who aren't familiar with it, this is the same sort of plot that basically won the Nobel Prize for the Hulse-Taylor pulsar. What it's showing is an orbital decay due to the emission of gravitational radiation in the system. And what the y-axis is showing you is the accumulated drift of the eclipse time compared to a source that's not changing its period. And what those negative numbers are saying is that the eclipse is happening sooner and sooner than you would expect for a source that isn't changing its period. You might stop me and say, wait a minute, Kevin, you said the period here is like 7 minutes. That's only a 414-second period, yet your y-axis here goes down to negative 4,000 seconds. Hasn't it already merged long before that? This isn't a change in the period. This is an accumulated error in the phase of the eclipse. And what that means is that this object has basically skipped many orbits compared to an object that isn't changing its period. So it's just skipped orbital cycles, essentially. And so these measurements are made by keeping track of exactly when the eclipse is happening over a long time scale. Again, a measurement made using only the eclipse. And I should say that part of this measurement was made by going back and digging into archival data from ZTF's predecessor, the Palomar Transient Factory, to pull out a much longer baseline track of what the eclipse was doing. And by the way, Rubin's going to be great for this sort of thing. The reason is Rubin will discover a lot of these by itself, but there will be some sources with too narrow of eclipses to blindly recover with Rubin's sampling. But when LISA turns on in the mid-2030s and shows us all the sources in the galaxies, we'll be able to go back to the archival Rubin data and basically piece together the evolution of the source over the previous 15 years by seeing what Rubin measured 15 years ago, because we'll have knowledge of the source position and its orbital frequency from LISA. And this is a really useful measurement to make, because by measuring the orbital decay rate in these detached binaries, you can basically say, if you assume that it's due purely to the emission of gravitational waves, there's a pretty clean expression of what that decay rate should be as a function of the trip mass and the gravitational wave frequency. And we already know the frequencies because we picked up the periodicities for these sources. That measurement is really complementary to the strain amplitude that LISA measures with the gravitational waves. And the reason is they both depend on the chirp mass in the same way. We know the gravitational wave frequency in both cases, so the additional degree of freedom in the strain amplitude is the distance. And so if you constrain the chirp mass by measuring f dot, you can actually pick out distances using the gravitational wave amplitudes for sources that are way too far away for Gaia to actually make reliable parallax measurements. And I should say there's another cool thing you can do. If you time these long enough, you can actually see the second derivative of their orbital decays. And by basically taking a derivative of that f dot expression towards the middle of the plot, you can see there's a pretty clean dependence that comes out. If the decay is due purely to gravitational wave emission, you expect that f double dot should just be 11/3 times f dot over f. And what we do is we try to basically measure deviations from that 11/3 to infer other effects that are responsible for the orbital decay in addition to GR, for example, tides, mass transfer, magnetic braking, etc. Again, these are all things that are coming from just studying the light curve of the source. So I hope I've convinced you at this point that this is a really rich form of data, and we should be pretty excited about Rubin delivering this for a huge number of sources. So now to get towards wrapping up the talk, since I know I'm getting further along in it, I want to take a step back and just show how revolutionary time domain surveys have already been in this area. So here's a plot from early 2018, right after Gaia started running and delivering parallaxes in DR2, just showing all of the known sources of gravitational waves in our galaxy that we know LISA should be able to detect. So that black solid curve at the bottom is LISA's detection threshold after running for 4 years. And what I want to say about these sources is most of these were detected through outbursting behavior. Basically, they were transient phenomena. And so very few of them are eclipsing. I've circled the eclipsing sources here. And I hope I've just convinced you that the eclipsing sources are particularly valuable by showing that example and everything you could do with it. So here are the sources that have been added in just the last couple years from ZTF. And so something I want to emphasize is those known sources took 30 to 40 years to discover. That was several decades of work to build up that sample. This is what we've done in just a couple years using a facility like ZTF. So it's just rapidly accelerated our ability to discover these objects. And one of the really exciting things, in my opinion, is that there's a pretty heavy bias towards eclipsing sources in this sample. And that's in part a selection effect, but it's a beneficial one because the eclipsing sources are so valuable. And I just want to say, we're not just finding a bunch of boring pairs of billiard balls that are all the same. These are all really unique sources. I can tell you a different story about every source on this plot. For example, just looking at a couple of the shortest period sources, that very shortest eclipsing one on the right is a helium core plus a carbon oxygen core white dwarf. That's different than the one next to it, which is a double helium core white dwarf. Those things had different evolutionary pathways to form. They will have different merger outcomes. They will have different mass transfer physics that happens when they interact. The one right below them is actually an accreting source with an accretion disk. It's the shortest known period source with a disk. The next one is a helium burning star with a white dwarf companion. And I could go through every single one of these sources and tell you a nice story about them, but I don't have time. I just want to emphasize it's a really rich sample. It's not like we're just building up a spreadsheet of everything is the same and now we're just doing population statistics. And so part of the program has been with these sources is timing them after discovering them. And so you can see orbital decay rates here measured for 6 systems, and I'm continuing to time more and more of them. But what I want to draw your attention to here is the plot on the right. I've done a very, very conservative estimate of kind of my most pessimistic estimate of what we should be able to detect using LSST in terms of LISA sources. And you can see there are a lot of them. So LSST will be revolutionary in finding these. And you should be a bit skeptical when I say that, because, you know, LSST has a smaller field of view than ZTF. And I've told you the story about how important sampling is. So maybe you don't quite believe me that you can do this with LSST. And what I want to convince you in this slide is that you can totally find these with Rubin. And so what I'm going to play is a movie here. On the left is a power spectrum of a source. In the middle is a light curve of it, phase folded at the orbital frequency. And on the right is going to be just the full light curve over the course of 4 years. This is real data from ZTF subsampled to the Rubin cadence. And so what you can see is with the first few samples, you don't see much. This is of the 7-minute binary, by the way. But quickly, as you get up to about 50 samples, you start to see the peak in the power spectrum at around 200 cycles per day. And by the time you're up to about 80 observations, it's quite clear. And you can see in the phase-folded light curve, the structure has already appeared. And I don't need to let this movie run for the full year, 4 years, to show you that you are definitely sensitive to these signals with Rubin sampling. And say there's a pessimist out there who says, well, most of these are going to be in the plane where the sampling will be lower, or maybe you're going to be stuck using only one filter. Well, so I subsampled it even more to show you, even with a sampling of only 20 to 30 epochs per year total, you still get it. It takes a little longer to build up the signal, but by the time you're in the 2nd year, you can already see the peak building up here. And I want to emphasize, this is not synthetic data. This is just real data from ZTF, where I threw away most of the data to simulate Rubin's cadence. So I'm very, very optimistic about my ability to recover these sources using Rubin. So I'm running out of time, so I'm going to skip this latest result and just say that there are other classes of sources, like very rare types of cataclysmic variables that we've been finding, rapidly rotating white dwarf merger remnants, black wrap up there to give a bit of time for questions. Thank you.
Thank you so much, Kevin. Super interesting science.